I want to run through what actually happens when we execute DML. What happens on disk? What happens in memory? There's some assumed knowledge here, by the way. I assume you are all database administrators. So there is some assumed knowledge. What I think I'll do at this stage is demonstrate what happens first and then return to the slide. So let me take, this is an absolutely standard 11G 11203 database, by the way, nothing special about it at all. If I connect to my database as user Scott, and I'm going to create a little table space. I'll create table space. I'll have a small table space. Data file, and I'll call the data file small one.dbf, size, let's just say 128K, can't get much smaller than that. Right, you'll see why I'm creating a table space specifically for this demonstration in a second. And then within that table space, I'll create a very simple table. Oops. A very simple table, T1, with one column C1 of varchar2 type. Now, insert a row into the table. So insert into T1 values, and I'll insert myself. Right. And I'll even commit myself. So I am now committed. Well, what's actually happened on disk? Let's take a look. Right, there's my data file, small1.dbf. Well, I've inserted myself and I've committed myself. Is there anything on disk at this stage? I'll use the strings utility to extract just the text strings from a binary file, and I'll string small1.dbf and grep out lowercase John. It's not there. And that's the first example of data corruption. I've got a committed transaction, committed, and it does not exist in the database. It simply isn't there. So right now my database is missing a committed transaction. That's straightforward corruption. But it gets worse. I'll insert another row. I shall insert a row. In this case I'll insert, who shall I put in? Susan. Susan can join my database. Right. Uncommitted transaction. So I've got a committed transaction which apparently is not in the database, an uncommitted transaction as well. Is that in the database? Well, it certainly shouldn't be. So we see if Susan exists in the data file, and sure enough she doesn't. But what if Oracle decides to write some data to disk? I'll go through the algorithm that we'll use shortly, but let us assume I'm going to force Oracle to write to disk at this point. So alter system, checkpoint. Force a write of buffers to disk. What's happened now? Susan is there. She exists in the data file. And this is as bad a corruption as you can get. Because think what's happening. My committed transaction that inserted John was not on disk. My uncommitted transaction that inserted Susan is in the database. This is a pretty serious state of affairs. Well, is it a problem? SQL plus, just connect from another session. And if I select star from T1, everything's fine. So I'm getting proper transaction isolation. My transaction that inserted John, well, we don't know how durable it is, but apparently it is pretty durable. It's there, it's visible, even though it is not in the data files. And my uncommitted transaction that inserted Susan is totally isolated, so nobody else can see her. Though, of course, from the session that did the inserts, that session is, of course, allowed to see the uncommitted transaction. Now, take a look at the next stage. What has happened within the redo log? I'll go through the redo log contents, and then we'll see how this has been implemented. Select star from v.log. So I want to see which is my current log file group. My current log file group is group 1. Right, well, group 1 consists of that file there, redo01.log. Well, let us see what there is in redo1.log. So I'll grep out John, and does he exist? Yes, he does. So the change vector that inserted John does appear to be in there. What about the change vector that inserted Susan? She's in there too, with a bit of junk either side. Well, maybe we can make things a bit more complicated, build up a bit more of an idea of what's happening on disk, and then run through the theory. Let's say in this session I shall update T1, set C1 equal, I'll put Dave in my database instead of me. C1 equals John. So do that update. Uncommitted. Uncommitted. What do we now see in the redo logs? Things get a bit more complicated. John has two entries now in the redo stream. One will be the entry when he was inserted into the table. The other will come from the undo segment when I updated the row, which we'll come to in just a second. And of course, Dave is in there too. Right. What's on disk? Well, right now, if we look at John is the person who exists in the data file. Curiouser and curiouser. Let us do a checkpoint to force the disk write. Alter system checkpoint. And what's in the data file now? John's gone. He's no longer in the data file, but Dave is. So now I have my uncommitted update has apparently wiped John out from the database. What's going to happen at this point if we have a problem and we corrupt the database? Okay, back to the theory. What I've demonstrated, we have the log writer and we have the database writer. The log writer writes on a very, very aggressive algorithm. Change vectors are written to the online log in very nearly real time. And when you say commit, it is real time. And as you've seen, pretty much as soon as I did any change, the change vector immediately went to the online log. Immediately. So I'll just commit that transaction. Stop any more confusion. But if I do another update, say I'll change Dave to Len. That's uncommitted. Oops, let me get this ready in advance. Grep Len. No mention, of course. Do my change. Set C1 equal to Len, where C1 equals Dave, and oops, small one, so I need to go to the redo. And in virtually real time, the change vector of the update is there. Also the change vector for Dave. He was there as well. Right, what's going on? Log writer, as demonstrated, writes on a very aggressive algorithm. Your change vectors go to the log file in nearly real time. And when you say commit, believe me, it is real time. Your session hangs when you say commit until the vectors have gone to the online log. And note the online log change vectors are both committed and uncommitted changes. Database writer, by contrast, also as demonstrated, writes on a very lazy algorithm. Now, I've changed a row to Len, but does Len exist in the database? Not at all. Database writer writes on a lazy algorithm as little as possible, as rarely as possible. Why? Because disk I/O is bad for performance. So blocks are written only if they conform to two criteria. They've been changed, because there's no point in writing data that hasn't been changed, and they're idle, i.e. no one's using them. And this choice of which blocks to write is not related to commit. End result, your database is always corrupted. As demonstrated, the data files on disk may be storing uncommitted changes, they may be missing committed changes. Does this matter? No, it doesn't, unless the instance crashes.